Hello and welcome back to the Energy Onion Energy Systems Engineering Training Certification, Chapter 6. For context, we have finished our introduction, including green, math, utilities, and accounting. We've been through lighting, HVAC, thermal energy storage, building envelope. We just finished industrial systems, and now we begin electrical systems, including motors and drives. As we have begun every chapter, we'll do the same here with definitions. The first three, amps, volts, and ohms, we're going to make parallels to something that is probably more intuitive to you, and that is with fluid flow or piping. The first definition of amps. Amps is a measurement of current, and current would be similar to flow rate, gallons per minute. Amps, gallons per minute. Volts in a piping or water flow situation would be like water pressure. Voltage is like pounds per square inch. Ohms is resistance, and ohms would be like the pipe size. You can imagine a much larger pipe has less resistance than a smaller pipe, or the resistive effect on flow and pressure is less than a smaller pipe. Watts is a measurement of power, and it's equal to voltage times current. We're defining ratio as efficiency, as a ratio of energy versus work out. Torque is, as you probably understand conceptually, it's a rotational force. Unlike a planar force, the torque includes what's called the lever arm. So torque, when turning a lever arm that is 2 feet away from the rotational axis, would be different than that same force turning a lever arm that is 1 foot away from the rotational axis. The frame size of a motor is just the physical size, but it is standardized, usually consisting of a NEMA-defined D and F dimension. D is the distance in quarters of an inch from the center of the motor shaft to the bottom of the mounting feet. D is that distance. The F dimension relates to the distance between the centers of the mounting feet holes. So you get those two dimensions, almost height and width, but more specific. Frequency is the rate at which alternating current reverses its direction. It's measured in hertz. We've used frequency earlier, but now you have the definition. Speed, as you know, is going to be in rotations per minute. An induction motor is simply a regular motor. As you'll see later, rotation in an induction motor is caused through an induced electromagnetic field. The inertia of something is the tendency of something to keep moving. And that's important as we consider braking power. A motor that's moving wants to keep moving. Insulation is classified by maximum allowable operating temperatures. So the class is what's the maximum allowable operating temperature, and it could go from 105 to 130, even 180 degrees C for a class H motor. The next three, constant horsepower, constant torque, variable torque, these are just to characterize a difference in load type. The phase of a motor is the number of individual voltages being applied. A single phase motor has one voltage in the shape of a sine wave, alternating current, applied to it. A three-phase motor has 3 voltages applied to it, and if you consider that sine wave, as we will, breaking that 360-degree cycle up, a three-phase motor would have three phases that are 120 degrees off with respect to each other, so that the peaks of voltage occur over time intervals and balance each other out, balancing the power received and delivered. The poles, you'll see as we look at the construction of an electric motor, poles are the magnetic devices that are set up inside the motor by placing by the placement and connection of the windings. If you take 7,200 and divide it by the number of poles, you'll get the motor's rotational speed in RPM. And the last definition, power factor, I'm going to leave that definition to when you see a drawing later, and you'll understand the active power and reactive power in the definition of power factor. So let's move on from these definitions now and get started. We're going to consider this picture of an electric motor. We have considered it in previous chapters. We'll look at it again in renewables, and that's because the basic construction and function of an electric motor looks a lot like a generator, depending on which two components you have. If you have a magnetic field and you have a current in that magnetic field, you'll cause rotation. In an electric motor, you have or create a magnetic field and you have current, and that causes rotation. That's a motor. In renewables, you'll see that you have a magnetic field and you have rotation, which will cause current. The next two slides include a two-phase and three-phase electric motors. These so-called polyphase motors have multiple current sources, multiple phases, and they energize separate winding coils, and that produces multiple current waveforms. So in this example here, you have a two-phase electric motor. If you take the positive of one phase, the negative of another phase, that amplitude then, that difference adds up to zero. So this is a two-phase motor. Let's look at a three-phase. This three-phase motor is similar in that you see multiple phases, multiple alternating current, positive and negative. When they're balanced perfectly, you get an amplitude of zero. However, since the size of the peaks is representing the voltage, when these phases aren't matched, these polyphase motors can give you a voltage imbalance. Before we look at the voltage imbalance, understand that the only reason you have a voltage balance is if the three phases sum to zero. So let's look at an example before we go to voltage imbalance. The blue phase, let's say, is at plus 1. At that moment in time, the green and orange phases are each minus 0.5. If those were slightly out of phase, slightly to the right, then they wouldn't add up to zero, and instead of having voltage balance, you'd have voltage imbalance. The voltage imbalance or unbalance is defined as the maximum voltage deviation from the average voltage. How far away is the maximum deviation from average divided by the average? And what this graph shows you is what effect does voltage imbalance have on the motor rating. If your voltage is imbalanced by 3%, you can derate your motor to only 90% of nameplate. If your voltage imbalance is 5%, you can derate your motor to 74% of nameplate rating. So what should we consider when we consider nameplate voltage, or the nameplate in general? The first thing you'll notice is horsepower. This happens to be a nameplate for a 3/4 horsepower pool motor. The voltage says 208-230/115. We'll discuss that in a minute. And then is the amp rating, the temperature rating or insulation class, ambient temperature 50 degrees C, insulation class. This is called a drip-proof enclosure motor. And then the frame size is L56J and insulation class B. And the last is it is a single-phase motor. Now, I don't believe that most of the people as attending this certification are going to be specifying motor replacement. So we won't discuss all the specifics on how to specify a motor and achieve the nameplate information that you need, but I wanted you to understand the data that's on the nameplate. The nominal voltage on the right shows a difference, typically a pretty consistent percent difference from the nameplate voltage. The reason nominal voltage is lower is because there is indeed a difference between voltage rating, the nameplate, and voltage supply, or nominal. And this difference allows for the voltage drop between the equipment and the supply. So what does it mean to have a desire that the power factor equals 1? Let's consider power factor along with efficiency as it pertains to load. Let's look first at efficiency. 1 horsepower, 10 horsepower motors. Both of them, you see that if they're underloaded, the efficiency goes down. Typically, a motor likes to be loaded between 50 to 100%, with 75% being a typical place to determine the high efficiency or the highest efficiency of a motor. Well, what this graph shows you is that power factor is similar. Similar meaning that if you underload, your power factor will be too low. With both power factor and efficiency coming up to 1 as their maximum, what this graph shows is underloading and power factor is a similar consequence to underloading and motor efficiency. We'll talk in a minute about what you can do to improve motor efficiency, but what can you do to improve power factor? Power factor correction, allowing the power distribution to operate at maximum efficiency. This power factor correction, you can see these two pictures and you can understand quickly why the electrical engineering of power factor correction is outside the scope of this certification. That said, however, there are some stratifications, some layers, like with chiller sizing, that can help put power factor correction in context. The first is for small power supplies, let's say less than 100 watts. The most common type of PFC, power factor correction, is passive. Passive PFC uses what's known as a harmonic filter, filtering out harmonics that is placed at the AC input, and it's used to correct power factor. For a design over 100 watts, the preferable type of PFC is called active power factor correction. With that said, and again reminding you that the electrical engineering behind power factor correction is beyond the scope of this certification, now is a good time to note that, in fact, many electrical utilities penalize customers for poor power factor. Since a utility is paid on the basis of energy consumed, and the reactive component, that vertical component on our graph, on our picture of current, doesn't register on a kilowatt hour meter, many utilities impose this power factor penalty to receive income for the total power they're required to deliver. Therefore, the decision whether to purchase power factor correction, should you spend your money on this electrical engineering? It's a simple financial calculation, just like should you purchase a lighting retrofit? Should you install window film? Should you replace your chillers? It's a simple financial calculation saying, what's the cost to me of having poor power factor, and what's the cost to fix it? And of course, use the financial calculators in Chapter 1 to determine a true return on investment calculation. The reason to show this motor system is we've been discussing so far efficiency and rating and power factor, but we aren't using just a motor. The motor is attached to something, which is attached to something, and there could be many things attached to this motor. And the input energy into the motor, there are some losses because of the motor. There are some losses because of the pulley and the belt and the fan, so that by the time you get the work out of your system, you have to account for these losses. And all of these losses are opportunities for savings. The reason we bring up the affinity laws is to put in context the previous slide that showed several losses. This slide shows that not all losses are considered equal. We'll say for fans or for pumps, the affinity laws are very similar. Just if you want to consider pumps, just use gallons per minute instead of cubic feet per minute. But let's consider the fans. Let's just use that one because of the similarities. What the first affinity law says is that the ratio of the cubic feet per minute after some change, CFM2 versus CFM1, is equal to the ratio of the rotational speed of the fan after versus before. So they are indeed linear. If you double the rotational speed of a fan, you'll double the cubic feet per minute. However, if you're considering pressure, air pressure, the air pressure after rotational speed change, it goes as the square of the change in CFM or RPM. And horsepower goes as the cube of the rotational speed or the cubic feet per minute. The reason this is important is horsepower is something that takes energy. A typical conversion might be 0.746 kilowatts per horsepower. So if you can indeed reduce rotational speed or reduce cubic feet per minute, you can dramatically reduce horsepower. We've considered how you can improve power factor. Now we turn back to how you can improve motor efficiency. There are basically two ways. You can either make a motor more efficiently convert electricity to work, or you can cause a motor to operate more efficiently. The first happens by looking at how the electrical energy you put into a motor, how much of it is translated into useful work versus unintended work or heating the surroundings. If you can reduce the unintended heat or work, you can improve the efficiency of a motor. The other way is operating an existing motor more efficiently. Using a variable speed drive, as we'll see in a minute, allows you to match motor capability, change motor capability to match the load. And this is true at any load, but particularly at low load, 5% to 40% load. You see on the graph on the right, a motor is working very inefficiently at that low load, but that efficiency can be dramatically improved through the use of a variable speed drive, through more efficient operation. The first equation at the top of this page, RPM equals 120 times the frequency divided by the number of poles. Earlier, I said RPM was 7,200 divided by the number of poles. Well, that's strictly speaking for 60 Hertz AC. When you consider the terms variable speed drive, variable frequency drive, the speed is the rotational speed. So you see from this first equation as well that a variable speed drive, variable frequency drive involves the same manipulation of speed and frequency. Now this long definition is worth your time and attention to understand the specification definition of a variable frequency drive. A variable frequency drive changes the speed of a standard AC induction motor by changing the voltage and frequency of the electricity supplied to the motor. Remember, the motor responds to what it's given. This is accomplished, this VFD accomplishes this by converting the alternating current AC to direct current DC, and then electronically manipulating and recreating a waveform that has the necessary voltage and frequency. And this technique allows a motor to be driven at any speed from standing still to full nameplate speed or even higher, what's called overdriving motors. So that output frequency is what changes rotational speed of the motor. The purpose of motor control is to extend the life of the equipment typically, and as a side benefit, or if possible, reduce energy consumption. To be sure, in most cases, the cost of premature replacement governs motor controls. Therefore, regardless of the energy savings, the control can't detrimentally affect the life of the motor. An energy management software or system is something that deals specifically with reducing energy costs and consumptions for buildings or communities. It collects data, reporting, monitoring, and reporting purposes include verifying energy data and so forth. Building automation describes the functionality provided by the control system of a building. We'll discuss building automation and control in the next chapter, Chapter 7. To summarize the electrical systems and motors and controls, we have to say again that remember we're getting into the back half of this certification. We're getting into more and more topics where the depth of the topic consumes careers for 40, 50 years. So we're not plumbing the depths of electrical systems, motors, drives. We're barely introducing them. And the reason is we understand the context of this certification. The energy systems engineer wants to be familiar with terms so that when they're in a conversation about electrical systems, motors, controls, that they at least have an ability to be engaged. Certainly you're going to defer to the experts in these systems when it comes to specification or troubleshooting. But you can have a conversational ability with these systems. For that reason, we've limited electrical systems, motors, and controls. And some of the main topics were the electric motor itself and the idea of single-phase, dual-phase, three-phase, and how that affects the amplitude and how voltage imbalance can occur if those phases aren't in phase. and the effect of voltage imbalance on efficiency and derating. We then talked about power factor, a very important concept, particularly if you have a power factor penalty by your utility. Now you understand why that they've put that penalty in, and you understand how to solve it and whether the solution is cost effective. We discussed affinity laws and how the non-linearity of energy consumption versus something like cubic feet per minute can cause tremendous savings in horsepower, kilowatts, kilowatt hours, if you can reduce that CFM or RPM. And then we discussed the variable speed drive or variable frequency drive, that component that allows for efficient operation even at low load.